Now we do few problems in the cylindrical coordinate system. We were considering the cylindrical coordinate system as an example of curvilinear coordinate system, and we had obtained unit vectors rho, phi and z in cylindrical coordinate system, and we had obtained expressions for gradient, for divergence, for curl in the cylindrical coordinate system. The unit vectors we obtained are these: rho cos phi I plus sin phi j, phi unit vector minus sin phi I plus cos phi j, z unit vector that is equal to k. Then the dou rho dou phi. We want to prove this dou rho dou phi. Dou unit vector rho dou phi that is equal to unit vector phi. And then dou unit vector phi dou phi equal to minus unit vector rho. So we are going to prove this. Okay. Then the dou rho dou phi, if I differentiate, this is rho, I differentiate this with respect to phi. So as I differentiate, I will be getting minus sin phi here, then cos phi j here. The minus sin phi I plus cos phi j is phi, unit vector phi. Okay. So dou rho dou phi that is equal to unit vector phi. Same way, if I differentiate the unit vector phi with respect to phi, that will be this. We know unit vector phi is this. So as I differentiate, I will get minus cos phi I minus sin phi j, which is minus of unit vector rho. Okay, so we have now proved these two results. Dou rho dou phi is unit vector phi, and dou phi, dou unit vector phi dou phi equal to minus unit vector rho. So let's move on to a second question. Rigid body is rotating about a fixed axis with a constant angular velocity omega. Take omega to lie along the z-axis. Okay, so we have a rigid body here, a rigid body that is rotating about z-axis. Okay, this is rotating. This is our rigid body. It's rotating about this axis. Okay. Okay, so its angular velocity will be along z-axis. Now what we have to do is, we have to express the position vector r in circular cylindrical coordinates, and using the circular cylindrical coordinates, calculate v equal to omega cross r, velocity v equal to omega cross r, and then we have to find del cross v, then we have to find del dot r, del cross r. Okay. Here r is a position vector in cylindrical coordinate system. Now to determine vector r in cylindrical coordinate system, actually we are going to perform all these operations in cylindrical coordinate system. So first we have to know the vectors r and omega. It is r and omega in the cylindrical coordinate system. So see this transformation. We already have this result. Unit vector rho that is cos phi sin phi. Okay, cos phi I sin phi j, that we know. Unit vector phi, that is minus sin phi I cos phi j, that we know. Unit vector z, that is equal to k. So I, j, k, so this is in the matrix form. So what will be I, j, k? That will be equal to cos phi sin phi 0 minus sin phi cos phi 0, 0, 0, 1, inverse rho phi z. Okay. So we have to find the inverse of this matrix. We find the inverse of this matrix, and it is simply the transpose. Because for this matrix, we have the A transpose A as equal to I. So if A transpose A is I, then A transpose is simply equal to what? A inverse. Okay? Because we know A, for any matrix, A inverse is unit matrix. So for such matrices, these are called orthogonal matrices. The A transpose is A inverse. So you can verify yourself whether this A transpose or A transpose A is a unit matrix here, that you can do. So the inverse here we need inverse. So that is simply the transpose. So that is written here, the transpose is written here. And from this we can get I as equal to cos phi rho minus sin phi phi. J is equal to sin phi rho cos phi phi, and k is as equal to z. Okay. So we can get I, j, k, these three unit vectors in the cylindrical coordinate system. Now our next job is to find vector r in the cylindrical coordinate system. Here vector r in Cartesian coordinate system is this: xi plus yj plus zk. So we have x we know, that is rho cos phi. For I am substituting this here. For I have this cos phi rho. So that I am substituting here, and this is rho sin phi rho plus cos phi, z unit vector z. Okay. Now as we expand this, we have rho cos square phi here. Rho here we have minus rho cos phi sin phi phi here. Rho sin square phi rho, then rho sin phi cos phi phi z. Cancel this, and as we combine, we get vector r in cylindrical coordinate system as equal to rho unit vector rho z unit vector z. So what we are noting here is r does not have phi component. Okay, r does not have the phi component. Only rho and z components are there. Unit vector component rho, unit vector z component z. So it does not have the phi component. Okay. So this is how we have the position vector in cylindrical coordinate system. Now the body is rotating about z axis. So omega I can write like this, omega z. This is the unit vector z in cylindrical coordinate system. So I have got omega. So we have determined vector r. We have determined vector z. Okay, so we have this V equal to omega cross R. We are determining rho phi z 0 0 omega. R is rho 0 z. Substitute. So we have rho 0 minus 0 phi omega rho z unit vector 0 0. Then V is omega rho phi unit vector phi. Okay, V, that is omega rho unit vector phi. All these terms will be 0. So we have got the velocity. Now once velocity is with us, we can determine del cross V. Del cross V, this is the expression 1 by rho. This here we need the rho component. Okay, the rho component. Here we need the phi component. Here we need the z component that we substitute. We know for this there is only phi component. The rho component 0. Okay, rho component 0 or the z component is 0. So we have this only. This and del cross V is now given by this. Okay, now we calculate this. As we calculate, we know how to determine the or evaluate the determinant. Rho, as we we take this will be 0. Here rho phi, this will be 0. And z, as we differentiate this omega rho square with respect to dou rho, with respect to rho we will be getting 2 rho omega. So that is written here. So what we finally get is 2 omega unit vector z. So this is our what? Del cross V. Then what is del dot V? We have this expression. Okay, we have this expression for divergence. We substitute. We need to find del dot R, not del cross. This is del dot V. Okay, we need to find del dot R and then del cross R. Okay, so del dot V is this, and using this we are finding del dot R. R is this, so we substitute the components. So as we substitute, we have this. As we differentiate, we will get 2 rho here and 1 and ultimately 3. We have the same result in Cartesian coordinate system as well. There we know del dot R is 3. Here also we get del dot R is equal to 3. And del cross R is 0 in Cartesian coordinate system or in any system. That the same result we get here, del cross R. Okay, here we know the components of R as rho z. We substitute and we will be getting 0 here. Okay, we have got 0 here. So del cross R is 0. So del dot R is 3 that we got, and del cross V and all these we have got. So we have now obtained, or we have seen how to determine position vector R and how to evaluate the divergence or curl or other cross product, other quantities in the cylindrical coordinate system.